Alright, so next up, let's talk about hyperbolic trigonometry. Hyperbolic trig functions specifically. We'll start with this little identity. If we have any function f of x, which has got a domain which is symmetric about the origin, we can write this funny little formula. 1 half plus 1 half is 1, and I've added and subtracted f of minus x. Well, who cares? Well, that... fascinating. Wow, interesting. All right, so, yeah, I'm leaving it. All right, so this is even, and this is odd as a function, right? If I put in minus x for x, and if I put in minus x for x here, this one goes back to what it started with, and this one brings out a minus. All right, so this is an even function, this is an odd function. When you apply this general principle to the exponential function, you get what are called Cosh and sinh, or hyperbolic cosine and hyperbolic sine. Here it is. Specifically, e to the x can be rewritten as 1 half e to the x plus e to the minus x plus 1 half e to the x minus e to the minus x. You're like, well, why are you making life difficult? I already know the exponential. Why do I need these two new things? Well, I mean, because I'm mean. But that aside, they're very useful, as you shall see. So here's their definitions. Cosh is 1 half exponential plus exponential minus x, 1 half exponential minus x for sinh. Fun elementary facts here. Cosh of 0 is 1 half e to the 0 plus e to the 0, which is 1. Hey, by the way, that's cosine of 0. Sinh of 0, 1 half e to the 0 minus e to the 0, but that's 1 minus 1, which is 0, which is, by the way, sine of 0. I hope you notice that I'm saying all of these things without a calculator, because you should be able to do the same. If you have to pick up a calculator or go to your book to look up these things, you're wasting your time. And yeah, I mean, yeah, you have a calculator in the test, right? But man, that's precious time you should be spending thinking about something more interesting. All right, with that said, let me go on to something more interesting. So Cosh and sinh look like this. Now, if you think about, let's see here, what else can we say? Well, there's lots of interesting things to say about Cosh and sinh. I'll just get straight to, let's see here, some big fun facts. Well, the graph of Cosh, basically, it looks like, what's the graph of sinh look like? Let's get to those first. All right. So Cosh looks kind of sort of like this. That's not doing it justice. It's exponential growth on both sides, right? Like this side, after a short while, is really just like 1 half e to the x. It's approximately like that, right? And over here, what dominates after a very short little while is 1 half e to the minus x. So it's exponential growth on both sides. And as I showed you, cosine of 0 is 1. And we can prove this with calculus, as I'll probably comment more on in future videos. Now, sinh of 0 is 0, and sinh is odd. It basically looks like this. I don't know, it looks like I'm drawing a cubic, but you should understand that this is 1 half e to the x, right? That's approximately y over here, and asymptotically this is like y is approximately minus 1 half e to the minus x. So it's exponential growth up and down both sides. All right, so just to sort of summarize things here, the range of Cosh of x is what? The range of Cosh x is 1 to infinity, right? The domain of the hyperbolic cosine is the whole reals. Likewise, over here, the domain of the hyperbolic sine is also all reals, right? The range is also all reals. All right. So this passes the horizontal line test everywhere. There's an inverse hyperbolic sine function. All right. So like you've got sinh of sinh inverse y is equal to y, and that's true for all y in the reals. And you know what? It's the same song and dance for the inverse hyperbolic sine of the sinh of x. It's also equal to x for all x of the reals. This is very kind of, I think, hard to mess up. Okay, there it is. Now, hyperbolic cosine, you got, again, an issue. I mean, globally, it's not invertible, right? So when we talk about inverse hyperbolic cosine, by default, we're talking about the inverse of the positive branch. That's the usual nomenclature. And so if we talk about, so here's definition, basically, Cosh of Cosh inverse of y is equal to y when. That only makes sense if it's in the range of hyperbolic cosine. That's going to be for y greater than or equal to 1, basically, all right? On the other hand, Cosh inverse of Cosh of x is only going to be equal to x again. That's going to be true for x greater than or equal to 0. Okay, so there you go. That's the definition of inverse hyperbolic cosine and inverse hyperbolic sine. And I'm not going to try to graph those at the moment, but you could. I mean, it just reflect these across the line y equals x, all right? All right, so that's the start of these things. Now, there's a few other basic algebraic identities I should mention while we're on it. So what else can we say about Cosh and sinh? How about this? What's e to the x times e to the minus x, right? Well, you know that that's e to the x minus x, which is equal to e to the 0, which is 1, right? But the thing is, e to the x is Cosh x plus sinh x, right? And e to the minus x, well, that's Cosh of minus x plus the sinh of minus x by definition, all right? And that should be equal to 1, right? But the thing is that that's Cosh x plus sinh x. If I was smart, I've written this before, but that's Cosh of x because Cosh is even, and minus sinh of x because sinh is odd, equal to 1. All right, so you got basically what's the pattern here? It's like a plus b times a minus b, right? And so you know that's the, this difference of perfect squares. Anyway, you FOIL it out. What you got is this, just this, Cosh squared x minus sinh squared x is equal to 1. This is the next best thing to the Pythagorean theorem. So this is analogous to, of course, we know cosine squared theta plus sine squared theta is equal to 1 for sine and cosine. So, hyperbolic sine, hyperbolic cosine, much the same, and yet they're very different. Anyway, there's lots more to say in terms of what are known identities for hyperbolic sine and cosine. Pretty much every trig identity there's corresponding hyperbolic trig identities. All right, I'll just say that for now. Let's see here. Other kinds of functions we run into are the reciprocal functions, right? And these come up a fair amount. So let me just list them. I won't try to categorize their graphs or anything like that, but you can pretty much figure out how they behave from what you know about sine and cosine and so forth already, right? So let's see here. For example, cosecant theta is defined to be 1 over, what is it? It's 1 over sine theta, right? Secant theta is actually 1 over cosine theta. Always bothered me that the s and the c are kind of flip-flopped, but there they are. All right. Cotangent theta is 1 over tangent theta, right? Which is, by the way, cosine theta over sine theta. So the places where cotangent is not defined is the zeros of sine, integer multiples of pi. All right. Let's see here. Are there any other? You can talk about the inverse functions of these as well. I won't get into it at the moment. And then, of course, there's corresponding hyperbolic versions of these. All right. So, like, what do we have? There's the hyperbolic. There's the CSCH, hyperbolic cosecant, which is 1 over sinh. All right. 1 over sinh theta. The hyperbolic secant, or I used x this time. Oh no. Now you'll be confused. Why am I using theta and then using x? They're just placeholders, all right? Hyperbolic secant is 1 over hyperbolic cosine, and then there's something called coth as well. Coth of x is equal to 1 over the hyperbolic tangent, which, by the way, is equal to, that ends up being, I guess I haven't defined hyperbolic tangent for you guys, have I? Oops. Anyway, so that's cosh x over sinh x. I mean, for what it's worth, tanh of x, of course, is sinh over cosh, all right? Now, there are identities which we know for all of these functions based on these two identities up here. In short, here's how you do it. It's pretty simple. You take these identities up here and you divide by different things. You get different identities. Like if I take, let me call it star, say star, and I divide by, star and divide by cosh squared. What do I get? I get 1 minus tanh squared is equal to 1 over cosh squared. Okay, but 1 over cosh squared is actually equal to hyperbolic secant squared of x. So there you go. There's an identity which happens to be known. 1 minus the hyperbolic tangent squared is equal to the hyperbolic secant squared. All right. And you could find another identity if you divided by sinh squared. That would give you an identity about the hyperbolic cotangent squared in relation to the hyperbolic cosecant squared, right? If we call this thing star star, you should know, I mean, very important identity. A very important identity is if you divide this by cosine squared, right? What does that give us? We get 1 plus tangent squared theta is equal to 1 over cosine squared theta, which is equal to secant squared theta, right? So there you have it, 1 plus tangent squared theta is equal to secant squared theta. Now you may have the feeling that I'm skipping some steps. You're right, I am skipping steps. This is calculus 2. This is a review. You're supposed to know these things already. And so if you need additional steps, well, come talk to me in office hours or something. I can show you. But anyway, so that's that. So I think that's most of what we need in terms of our standard, library of functions that we like to do calculus on. We also have algebraic functions, square roots of things, and we'll have rational functions, ratios of polynomials, and all those things. We'll talk about those as we get to them. These are the main things that you need to know definitions for and the basic graphs of so that you can do analysis, right? So anyway, with the next video, I will start into calculus. Thanks.